All right, welcome back. Today's lesson is going to talk a little bit about some of how we have come to understand the structure of the atom. So we're going to take a look at kind of a little bit of a romp through history here, trying to look at some of the different kinds of things that scientists have thought about how the atoms are put together, some of the important people that were involved in this process. I affectionately call this the dead white guys. So keep in mind that the couple of things I need you to know from this is the names of these about 5 different people that we'll talk about today, the major advancement that they made towards understanding the atom. So did they discover the nucleus or the electrons or whatever? And then what was the name of their model? So I'm going to ask you to be able to do things like sketch something or identify a picture of one. So, all right, moving on. So we're going to start way back when. We're looking back 400 years. BCE, so basically 2,500 years ago. The first 2 guys that we're dealing with this are some of the Greeks. We've got over here on the left, we have the epic rap battle between Aristotle and Democritus. You may have heard of both of these gentlemen before. Aristotle's a famous guy. Democritus, you know, there's this kind of famous thing that's named after him called, I don't know, democracy. Anyway, these 2 guys were philosophers thinking about how the world was put together. And Aristotle was actually quite a bit more famous. And so his wrong ideas took about, 1,500 years to basically get rid of. Aristotle was the guy that came up with the old-fashioned elements like you're used to, air, fire, water, earth, and dealing with those sorts of ones. And Democritus, who lived at basically the same time, was kind of a crazy dude, apparently. They called him the laughing philosopher. But he had some weird ideas that atoms, matter, was made of these funky little ball-shaped nuggets called atoms. He actually invented that word. That's his term. So the important dude here, Democritus, invented the word atom. And his idea was that atoms were these tiny little nuggets of matter and that every different type of material in his world had a different kind of atom that made it up. So that's what we have to thank for him. Unfortunately, this poor dude wasn't given any love for, like I said, about 2,000 years. Poor guy. And then this dude came along, not just a couple years later, only in the years, 1800 or so. We have this dapper-looking fellow over here, John Dalton. Sexy beast, isn't he? Look at those glasses. John Dalton was kind of what I would consider to be a first true chemist. There's lots of people working in alchemy before him. You have seen this guy's picture and some of his symbols for elements earlier this year. But his idea for atoms was basically to essentially reinvent Democritus's idea, which is that atoms are basically little indivisible nuggets of solid material. His model is called the billiard ball model. If I could talk, that would help. But that each different atom had its own little type of material, like I said, very similar to Democritus's idea. And he was the first guy to really study different types of atoms and start to try to quantify the different kinds of atoms that he called elements, and then to even start to look at how atoms would react together to form what we now call compounds, and that they would come together in these particular things that we call chemical reactions. So that's why I call him the first true chemist. There's obviously plenty of other guys in between, but he invented a lot of our modern ideas about elements, compounds, chemical formulas, and then some basic ideas about reactions. So John Dalton, the billiard ball model. Our next guy, I want this pair of glasses actually, the sort of monocle style. This guy's name is J.J. Thompson, and J.J. Thompson came about 100 years later. There's a lot of work being done by Dalton and the people that after him about trying to figure out what reactions were. And J.J. Thompson was the first guy to start to try to figure out what was inside an atom. Could you take an atom apart? And he was working with these funky things called cathode ray tubes. You can see one here. A cathode ray tube is actually the center component of old televisions, CRT type monitors, those big ones, not the flat screens like we have today. So actually his work with these cathode ray tubes really changed our modern world forever. But one of the things that he discovered when you run electricity through these cathode ray tubes was that there's this kind of funky greenish glow that came through here, which, okay, fine, there's a greenish glow. They thought it was light was exciting. And then you do this. I don't know if you've ever taken a really strong magnet and held it near a flashlight, but that certainly is not what happens. This greenish glow actually bent, and this was a very unusual thing, and it took him a lot of time to try to figure out what was going on here. He knew that this ray that's in the middle, this center part, had something to do with atoms, but he didn't know exactly what it was, and the fact that it curved now meant that it was interacting with a magnetic field. And now this shouldn't happen because they knew that atoms were neutral. So what in the heck was going on inside this element? So his experiment's the cathode ray tube. On the next screen we'll talk about what it was that he discovered. So here we go. All right, so here is Thompson's version of what he used to explain that greenish glow. His model is sort of lovingly called the plum pudding model because he lived in the, early 1900s in England. This is not a name that we would use today. Most Americans call it the chocolate chip cookie model, the blueberry muffin model. But anyway, his big thought was that when he had this greenish glow, he knew these charged particles were coming out, and these charged particles had to have something to do with inside the atom. Furthermore, he knew that these charged particles were negatively charged based upon the types of magnets, so to speak, that he exposed them to. So he came up with this idea that an atom, instead of being truly neutral, was actually made up of smaller parts. So J.J. Thomson's contribution is that he invented the idea of subatomic particles, and the particle that he discovered was these little negative dudes in here, which we now know are called electrons. That's what he invented, was the concept of electrons, and that atoms were divisible now into smaller components. And you can kind of see why it's called the chocolate chip model, is that he thought that atoms were made of sort of this positive kind of background cookie material, or if you want to think about watermelon, the red part of the watermelon. And then he thought these electrons were the things that he was knocking off, this greenish glow, that somehow he loosened those up with the electricity, and that that's what was actually traveling from left to right down that tube, and those electrons were then attracted to the magnets. So you could think about the chocolate chip cookie model as the chocolate chips being the electrons and the cookie itself being the positive background that he called protons, or I think he called it, he had some other name for it, the matrix, the sphere of uniform positive electrification. I think I like protons better. He did not know what protons were, though. That was not his idea. Again, his big idea, the plum pudding model or the chocolate chip cookie model, and that there were these negatively charged little nuggets in there known as electrons. So the first guy to discover subatomic particles. Okay. Problem with his model, that the guys that came after it, is that if this was true, if we really just had this sort of model of a cookie with these negatively charged things in there, there would be no way for this model, this atom, to actually stay stable over time, because eventually, kind of like you see in this drawing here, these electrons would start to kind of collapse. They started realizing that something else was going on with what was happening in there. So there was an issue with these guys that came up next that said, well, you know what, Thompson, we love you, man. We get that there's something positive, we get that there's something negative that's out there, but these things are just going to fly together. Something is definitely not going to work if we have the two different things kind of coming together in this particular piece. So let's take a look at the next what model that they started to try to figure out what these are. So this next guy that came along, another dapper looking fellow, look at that mustache. This guy is Rutherford, and we've talked about him briefly before, but he actually worked with a guy named Bohr, who I know we've talked about, and these two guys were actually trying to figure out what was going on inside the atom. How is it possible that with Thompson's model like this, that the atom itself didn't kind of collapse and come apart, and then how did it behave? So the famous experiment that he's got that I'm going to ask you about is something called the gold foil experiment, where he took a very thin piece of gold foil. It could have been any metal, but gold worked well because it was very, very dense. And then he took basically a laser beam, not really laser because it was actually made of particles. So these are called alpha particles, but they are really high-level radioactive source, basically. And he shot these laser beams through this piece of gold foil. And what he expected was, if the Thompson model was true, then kind of like in this diagram on the bottom left, that if he was shooting these little particles through there, they should pretty much come straight through. And this is not what he found. He found that a lot of them came pretty much straight through, but some of them started to kind of scatter, is the term that they use. And then even weirder was that some of these started to bounce way back. He put this fluorescent screen that's around here, kind of a funny spelling, but he put this fluorescent screen around the outside so that every time one of these particles would hit it, it would have a little flash of light, so you could see exactly where these things were landing. So again, if it was Thompson's model, they should have been just going kind of pretty much straight through, nothing too much going on. But these ones that bounced way back or that bounced scattered off to the side were really surprising. And so he actually invented the next idea in terms of understanding what was going on, something that you'll recognize. His job was to recognize something that he called the nucleus. That's Rutherford and Bohr. These guys worked together on this. But his job was, the way that he interpreted the results of that gold foil experiment was that, like this picture up here, that if it was Thompson's model, those particles should have pretty much just shot straight through. But they didn't. They bounced off. And the only way he could think about it bouncing off was to postulate, to hypothesize, that all those positive charges had to be collected in a dense center of the atom. That if they were spread out, like Thompson thought, these particles should just go right through. But the fact that they were collected in the center would explain some of these weird bouncing off or some of these crazy deflections that he saw as these alpha particles kind of got close to that dense center, but maybe didn't pass straight through it. So his term for that, and he and Bohr worked together on this, he decided to call it the nucleus. And I know this picture right here is that classic, Jimmy Neutron model of the atom that people still classically think of as what an atom is. And that's Rutherford's idea, or Rutherford and Bohr together came up with that idea, that there has to be a nucleus in the center of an atom, and that those electrons are still out and around, but they're not kind of evenly scattered throughout, and that the protons, the positive part, have to be someplace else in the center. So again, big idea between Rutherford and his buddy Bohr. Rutherford's experiment was called the gold foil experiment, but his big discovery was the discovery of the nucleus from these weird deflections that the positive charges had to be collected in that dense center called the nucleus. So that's Rutherford's big contribution. And then Bohr took it one step further. Now, Bohr and Rutherford worked in pretty much the same lab. They worked together. So these models are very similar. And we've talked about Bohr in class before, that as he was studying even further about, how these electrons moving around, his work with emissions spectrum, in other words, taking up hot gases and seeing what colors of light they release, he realized that those electrons and those colors that were being produced by those electrons had to be related to an idea that he came up with called energy levels, that those electrons weren't just in kind of crazy weird orbits this way, that they had energy associated with them, and that those electrons could absorb and then release energy depending on how they moved through those particular energy levels. So Bohr's model of the atom and Rutherford's model of the atom are very closely related to one another. In fact, like I said, they worked at the same time. They both worked together to develop these models. So that other one was, with the crazy kind of oval shapes to it, is oftentimes also called a Bohr model, Rutherford Bohr model. But the one I like to call the Bohr model is more of this one, this planetary system, where he's thinking about it in terms of orbits, or more like energy levels, as opposed to kind of them all flying around in these odd sort of patterns. So this is a classic version of kind of what the more later version of this model looked like, which they called the planetary model or the solar system model, where you had the nucleus in the center, which was consistent with what Rutherford found, and then the electrons had to be in energy levels around the outside. And these electrons had, energy levels, had different sizes. So the smallest energy level, the closest one, had 2 electrons to it. The second energy level could hold up to 8. The third energy level could hold up to 18. So this is a very commonly used drawing of electrons, or atoms, that we use all the time. Actually, we'll still use them in class from time to time to kind of get us a better idea about how electrons are sort of distributed throughout an atom. So anyway, Bohr's model, again, that idea of the planetary model, that there's energy levels, that those electrons are not just sort of moving randomly, but they're organized into energy levels, and that there's different numbers of electrons that can be in different energy levels. Last but not least, this modern model of the atom has been throwing people off for a good 50 years. It's called the wave mechanical model, and we'll talk about this more in class because it's pretty complex and very hypothetical, very abstract. But just to get some basic ideas of taking Bohr's model and sort of making it fuzzier is kind of a really good way of thinking about it. Bohr's model was highly organized with electrons moving in energy levels, moving in nice neat circles or nice neat patterns. Well, these guys came along, and you maybe recognize this dapper looking fellow, that's Einstein. And then this guy over here, his name is Schrödinger, one of the coolest dudes on the planet, worked with a variety of other guys like de Broglie, Heisenberg, a guy named Planck, a variety of other dudes that lived all, in the 50s and on. As they were thinking about how electrons move, they started to realize that the electrons move in a much more chaotic fashion, predictable but chaotic. And so they took the element of organization out and put the element of chance and probability back into this. And so we can't say that the electrons just move in a nice neat circle. All we can do is say over time, electrons are more likely to be found in sort of this sort of range. And this is now kind of how we think about what an energy level is. An energy level is just a zone where electrons are likely to be found, not just a nice neat path that an electron moves around in. So if you take a look at this one over here, this is what we would call the electron cloud, right? Where you've got different regions on the inside and a second level or maybe even a third shell on the outside, where these electrons can be sort of found in these different spots in here depending on which energy level that they're in. But again, this is a much messier idea of what an atom is. And with electrons, it kind of went from being highly organized to being almost highly disorganized. The big concept here, the concept of chance and probability, that we kind of know where electrons hang out, but man, they're a lot more difficult to work with than we really thought. And so any of our nice, neat ideas like Bohr had about electrons just cruising around in these nice, neat circles, throw that right out the window. This is all about probability and where electrons could be, not necessarily where electrons are. So again, this region is called the electron cloud, and this whole model is called the wave mechanical model. I'll explain more about why the wave word's in there when we get into class. And then last but not least, over the last few years, we've even started to take these particles apart. We now know that there's protons, we now know that there's neutrons, we know that there's electrons. Well, now we start to realize that we can even divide these further into more fundamental type particles. Those particles are called quarks, and even quarks can be taken apart into smaller things that I won't get into here. But a quark is a subatomic particle, and it turns out that neutrons and protons are sort of different combinations of quarks combined. Like down here, this is a proton consists of 3 quarks, 2 up quarks and a down quark, as opposed to a neutron is composed of 2 down quarks and an up quark. Weird, right? And that's the difference between neutrons and protons. An electron appears to be fundamental. It is a quark all of its own, a different type entirely, but it's its own fundamental particle. And one of the reasons I threw this particular picture in here was just to give you an idea of really how much space there is within an atom. That atoms, yes, have structure, but they have a whole lot of chaos as well. My favorite part is this part down at the bottom. I know it's really hard to read. So if you took each one of these little dots here, that was a proton and a neutron, and you made this 10 centimeters across. Now 10 centimeters is about the length of your pen. Think of it that way. 10 centimeters, a little shorter than that, but you know, something in that range. That would mean that the electrons themselves, the single electron, so this is 10 centimeters, about a pen, right? An electron here would be 1/10 of a millimeter. Remember, a millimeter is 1/10 of a centimeter, so 1/10 of a tenth. Really, really tiny by comparison to a proton or a neutron. These are absolutely microscopic. And then furthermore, if we tried to make an atom of the same scale, where a proton was about the length of your pen, the entire atom would have to be about 10 kilometers across, several miles. It's amazing to think about that. One of my other favorite images is to think of a baseball stadium, like a Major League Baseball stadium, that if you had a couple of marbles sitting on, you know, dead center, pitcher's home plate, whatever, pitcher's home plate, really? The pitcher's mound or home plate. If you had a couple of marbles sitting down there, then an electron would be about the mass of a cotton ball, but invisible. And then the electrons would fill up the rest of the stadium. That's the idea of the electron cloud model, that you have very, very small objects moving very, very fast and filling up what's essentially empty space. So I hope this is kind of giving you some ideas of some of the main guys to talk about or to think about, and we'll kind of go over these in class tomorrow to give you the big ideas. So you've got Democritus, our early Greek, that invented the word atom. We've got Dalton, who had the billiard ball model that atoms were solid objects. We've got Thompson, who came along and discovered the electron based on his little greenish glow, followed up by Rutherford's gold foil experiment and the discovery of the nucleus, and then Bohr's refinement of that and discovery of energy levels around, and then finally with the more modern guys, the wave mechanical view of the model, which is based largely on probability, similar in terms of the nucleus, but the electrons themselves are much more nebulous, that they're floating around in sort of a cloud, but basically moving around at the speed of light. So kind of a crazy idea what we understand now. All right, I hope you've enjoyed this a little bit and learned something about the structure of the atom and are coming to understand it over the last, 2,000 years or so.